let me tell you, quickly finish up the one thing I didn't talk about last time, which was the non-relativistic case of what happens if you have spin 1/2 fields, if you have spinor valued fields. So it's a fairly straightforward, enhancement of what you had in the case of just the standard solutions of the Schrodinger equation. And then we'll start, we'll soon get to kind of completely different material, which is going to take most of the rest of the course, which is what happens in the relativistic theory. So if you have a relativistic quantum field theories, how do those work? So we'll start going into kind of the geometry of Lorentz space, of Minkowski space, and the Lorentz group, and start explaining some kind of the new. You basically replace everything I've been talking about that we did in terms of the Euclidean group. We'll do for a space-time symmetry group for the Poincare group. So that's where we're going next. Okay. Okay. So let's see. So the so last time what I was telling you about was really the three symmetries of the non-relativistic quantum field theory. So in other words, so the basic theory is so this is just the free So we're just talking about free particles in the non-relativistic theory. And non-relativistic really means that you've got so that the energy is so the energy is it's a free theory. The energy is just the kinetic energy, half mv squared, or if you like the length of the squared over 2m in a free particle. And this theory is invariant under translations. This isn't x dependent, and it's invariant under rotations. And then, as I said last time, so then the whole question was about, once you've defined this kind of multi-particle formalism of Fock space with annihilation creation operators and field operators that create and annihilate quanta, either quanta with a fixed momentum or quanta with a fixed x. How do you use those operators to write down, that for any element in the Lie algebra here, you should be able to write down an operator which gives the representation of this group on the states. And we went through that last time, and I think so it was kind of say so what you have really is that so momentum. Which is the translation symmetry here gives you there's an operator which you can write as either integrate over R3. Just one way to think of it is just the annihilation and creation operators. But then you put in you basically weight these things by the momentum. So you're summing over all possible momenta, just the number operator at that momentum times the value of the momentum. That's what it is. Momentum space in position space. It's then just minus I think the gradient operator. Okay. So anyway, so you need to make these the main trickiness about these things is that since this is you now have an infinite dimensional phase space, an infinite number of oscillators. That these things really only really make sense as kind of distributions, and you have to make sense of that. But other than that, they're fairly straightforward formulas. And then you have that the angular momentum is the same thing. Where just instead of the momentum, you just take the your standard formula for the angular momentum, which is the generator of infinitesimal rotations, which is the cross product of the position and the momentum. And so here you can't. So here you diagonalize the momentum operator here, and it's not non-diagonal in the in differentiating sphere with respect to x. But you've got when you try and do the angular momentum operator, it's not going to be diagonal in either picture. You can either write the angular momentum operator in terms of x or in terms of p. They're related by Fourier transform, but it's going to have two pieces. One that depends upon x, one depends upon p, and only one of them is going to be diagonal. So, but for instance, if you do this one, it's going to be cubed. Okay, so it's just it's the standard expression for the angular momentum operator that you're used to from the just kind of the operator with one derivative, which tells you how to rotate. Okay, so now so this was the story what I was trying to tell you about last time, and what you should be able to show is that these guys satisfy the commutation relations of the algebra of the rotation group. I mean of the Euclidean group. These guys commute with each other. The commutation relations of this and this are what you get by infinitesimally rotating vectors, and this guy, different components of the angular momentum. That don't commute with each other, but they satisfy the SO3 commutation relations. So you should be able to show if this is doing what it's supposed to do, that's reflected in these commutation relations of these guys. Okay, so now that what about this is kind of what we call the spin zero or the scalar particle. It's just, but now what about spin 1/2? So what if we want to? Oh, and also again, the thing to say is that I haven't actually. This is this formalism also works with commutation or anti-commutation relations. So these guys could in principle be bosons or fermions, but scalar bosons or fermions. And it turns out that there's a theorem which says that that in a relativistic theory, if your scalar particles have to be bosons, they can't be fermions. And we may get to that later in the class. But in the non-relativistic theory, it turns out there is no such theorem. Non-relativistically, it's perfectly possible for your scalars to be either bosons or fermions. And it's all the same formulas, just the opposite commutation relation. Okay, then spin 1/2 particles, so they have the opposite behavior. In the relativistic theory, spin 1/2 particles are going to have to be fermions. But in the non-relativistic theory, you can have spin 1/2 bosons or spin 1/2 fermions. It doesn't matter, but you just have to figure out how to generalize this story. And what you need is so here you have so E3. Well, so E3 is translations and rotations. But if you want to talk about spin 1/2 particles, you can work with the same Lie algebra, but for the Lie group, you have to take to get it to act on spin 1/2 things, you have to take the double cover of this. So here you have to go to this double cover, which I think sometimes I'll call E3 tilde, but what it really is R3 semi-direct product spin 3, which is SV. And so it's just so you're just taking the double cover of SO3, the standard double cover of SO3, and the it's a standard kind of semi-direct product. That's the spin 3 acts on R3 just by rotations, by the spin 1. Anyway, so it just acts on this by rotation. So the action of this on this factors through SO3, but you have to go to this group if you want to talk about spin 1/2 particles. Okay, so now how do you explicitly write down spin 1/2 particles? Here he's doing it. Well, so what you do is you take, so go instead of, so you consider C2 valued wave functions. Okay, so far we've been talking about just complex valued wave functions, and value wave functions. So if you like H1, well, so we can take H1 is just going to be the same thing that we had if you. Well, I should even say not necessarily not necessarily L2, but anyway, some space depending upon whether you might want this to be a short space, but at the biggest one that's going to completely make sense is L2 of R3, and then but if you want to take things that have two components, you can think of it as the tensor product with C2. So there are going to be things of the form, and write down things of the form vector. And we can think of this as being t is equal to 0 initial data, specifying a solution of so these corresponds to solutions, two component solutions of the Schrödinger equation. So it's the same equations, but just with two components. Or I showed it that in this case, when you had two components, what you could do is you could show that the this p squared over 2m operator actually had a square root. That you can take a square root of p squared, which is sigma dot p, and then you can think of it in terms of that, and that's often called the or of the Pauli-Schrödinger equation. But as long as you don't couple the spin half particle to electromagnetism or anything, you're not going to actually see. It really just is the same. There's no operator in the Hamiltonian isn't mixing psi 1 and psi 2. So it's really just two copies of the standard free particle theory. So the only thing that's different is that the rotation group, now you have to go to this double cover, and you're going to have and when you ask how our rotation is going to act on these wave functions, so you're going to have that rotation that S spin 3 acts on wave functions. So what you've got, or it's SU2. So you've just got group elements here are just 2 by 2 complex unitary SU2 matrices. So you're going to have psi 1 goes to. So the way they're going to act on here is by these rotations, And again, it's the, so it's R inverse X. Okay, where R is, so, and let me call this, I guess I call this omega here. So omega SU2, and then R is, you take R is the rotation you get. So if you take if you act by omega, what's the right way to say it? So I want to print the how does the map go? It goes from SO3 to SO2. So you want an SO3 element that corresponds to omega. So I guess it's just oh, let me just say. So this guy, each of these guys, there are two of these guys corresponding to each one of these. So this is just the corresponding rotation, and that corresponds to, and you're going to have this guy or minus this guy will give the same actual rotation in three-dimensional space. But the new thing that happens, so instead of just what happened before, which you just had rotations in space, and these were the infinitesimal generators with the angular momentum. Here you've got the angular momentum going, but you've also got this guy acting, and so so what's happening is that this, as far as this piece of the tensor product is concerned, you're just doing it's exactly the same as before. But as far as this piece of the tensor product is concerned, you're multiplying, you're acting with this SU2. Okay, and then so infinitesimally, what happens is all that really happens is this: is that everything. So the formulas for the as far as the translations are concerned, nothing new is happening. It's just the same translation operators. But as far as rotations are concerned, you have so now you get so infinitesimal. So the Lie. Well, so rotations now. So rotations are, you should think of now as being things in SU2, and so infinitesimally it's the same Lie algebra. It's the same R3 Lie algebra, but you have L. What you used to have, this L vector now goes to J vector, which, and remember when you take the Lie algebra acting on a tensor product, you end up with, you get the action of, you get two pieces. You get a piece of how this is acting on here, and then acting trivially on there. So maybe let me write it as L vector tensor the identity. So it's acting trivially on here and there, plus a piece which is the identity on here and acting non-trivially on there, which is called S vector. And S vector is just the infinitesimal version of this SU2 action on the spinors, which is so S vector is a half sigma. It's this guy. So what's going to happen is that you're the operator that's going to have the right commutation relations, that's going to tell you how these how these spin transformations act on the whole system is what I call J vector hat. It's going to be just the three. Okay, so this is now a maybe I'll, well, so one. Okay. And then I guess there's going to, depending on X, and then there's going to be a it's going to be this thing, but here I mean this x vector across vector plus 1. Now I feel confused myself. Anyway, all you really need to do is to say this guy. It's this guy plus 1/2 sigma vector. Anyway, so I'm just trying to write down that the same formula that you would have, just two copies. This is just 2 copies of what you had before, but then there's this extra term here which mixes which can mix psi 1 and psi 2, which is this guy. But this is just your orbital angular momentum, and this is your spin orbital spin angular momentum. And again, you should be able to check that this guy. If this works, this guy the components of this guy should satisfy the SO3 or spin 3 Lie algebra commutation relations, and it should act on the momentum operators by a rotation. Okay, so that's pretty much the story. So there's one other thing in here which I really maybe I'll say more about this later, which is so the one thing which is funny with this is that I said so if you go back and ask, okay, so what's the story about irreducible representations of E3 or of this double cover of it, that we if you go back to what I told you about those, I said that the spin 1/2 doing this actually gives you 2 irreducible representations of E3 tilde, one with positive helicity 1/2 and one with negative helicity 1/2. But so the problem, this formalism isn't very good for this. It doesn't. This is kind of a copy of 2 irreducible representations, and because this isn't diagonal, you don't have they're kind of mixed together. So if you want to separate out the helicity 1/2 and the minus 1/2 and the helicity minus 1/2 and the helicity plus 1/2 components of this, so that you're looking explicitly at irreducible representations of E3, you have to do something else. You have to kind of pick some. You have to pick a kind of a p dependent basis, not use this psi 1 psi 2 basis, and to get helicity eigenstates. So that's in the notes, and maybe I won't say more about that now. It's just one reason that I put that in there now is not that that's at all a very useful thing to do in this case, but when we get to a relativistic theory, then what's going to be happening, there's going to be a relativistic analog of this, and we're going to then we're going to need to kind of understand how the states break up as irreducible representations of the space-time transformations, and so that will become important there, even though it's not actually a terribly useful thing to do here. Okay, so I think maybe that's that's pretty much all I wanted to say about the non-relativistic theory. So are there any, before we can move on to something completely different, are there any questions about anything about the non-relativistic theory? So it's all, but I mean, what I'm doing is it's kind of physically trivial. These are just free particles, but it is a legitimate formalism for talking about arbitrary numbers of particles with arbitrary different momenta and positions, if you like, and understanding how the different how all the different symmetries work on that. Okay, so then if not, let's go on to relativity. So far, if we're working non-relativistically, what we're doing is we're thinking about space and its symmetries completely independently of time. Time is just some separate thing with a real symmetry. I mean, there is a larger symmetry group you can try and play with of the non-relativistic theory called the Galilean group, but that group is anyway. I mean, there's nothing terribly useful about that group, and there's actually some subtle. If you try, it actually has some subtleties. If you try and think about the group theory involved there, also, so it's both a slightly tricky thing to work with, and it's not very useful. So, if you anyway, so there is a way to put time and space together in the non-relativistic theory and look at a bigger symmetry group involving both, but I don't think it's a particularly useful one. Whereas in the relativistic theory, the time and space will go together in a way where there is a very, very nice way of thinking about the symmetries of time and space together. Okay, and okay, so this is all special relativity. And maybe the crucial things are that you're going to consider time and space. There R3 space plus R time as an R4. And one thing to note is that we'll find that E squared is equal to I want to take P squared plus M squared instead of So the other crucial thing is going to be the relationship between. So what we're going to be doing is we're going to look at instead of the free particle Schrodinger equation where you get this energy momentum relation, we're going to be looking at relativistic relativistic wave equations, and for these relativistic wave equations are all going to have this property that the energy momentum relationship is that the energy squared is the momentum squared times the C would normally be set equal to 1 from now later on, but anyway I have it here, and then there's a mass which may or may not be equal to 0. But you can check that in the case of for the mass non-zero, for in the limit of low momentum for P small, as P goes to 0, the first order linear approximation to this quadratic equation is just this guy. So this is what we've been talking about is in some sense going to be a limiting theory to the theories that we're talking about, that we're going to talk about next. But in the case of as the momentum is small compared to the mass. Okay, so what are we going to? So what we want to do is look at this R4, and so the idea is consider, and I guess it's called Minkowski space. Which is R4 with inner product what is it? X. What do I call it? Do it here. So X. So X, Y. So these are both elements of R4, and you can write them as minus So you write the usual equation for the inner product of two vectors. But now if I write just x and y without normally if I put a little vector hat over here, it means I'm talking about vectors in R3. If I leave it out, I'm talking about just a vector in R4. But this is the so this is the standard thing. But then you do something funny, which is you change sign on the time components. Okay, and so one thing to notice is there's an alternate convention is it would be to put the sign on these guys. Okay, so you'll find more or less, I mean, very roughly, half the people who do this work with this the way we do, and half are gonna use this instead. And there's anyway, so the part of the cultural thing is people who worked in particle physics, at least since coming up into certain traditions, you would use this because it made minus signs come out nicely in certain places, whereas other people in particle physics coming from who were trained by different other people who like to use the plus, or people who worked in general relativity, came out of general relativity would use this. And so I'm gonna anyway. This is what I'm happiest with for various reasons. The main reason that this makes me happy is that what this is saying is that you really, to me, is that you should just be thinking of this as a usual notion of distance, except that you want to do something really funny with time. So if you're at a constant time and you're looking at things where there's no time distance, then it's just the usual inner product. Whereas if you work in this convention, then at t is equal to 0, you've got a nice R3 with whose inner product is negative definite, is negative the usual thing, which makes it hard to see what you're doing. And what I should, I guess, but anyway, there's some other things with this. At some point, if you look it up, I actually wrote a long semi-joking blog posting about why this is absolutely right and people are doing this are wrong, and partly in order to try to get a reaction out of some people, and that was kind of successful. So there's kind of a long discussion. You can get people to argue a lot about that there. I just actually noticed on Twitter yesterday there was somebody was posting something like what's the shortest thing you can do that will annoy certain other people in your field? What's the shortest tweet? And somebody had just put up the I guess either this, or somebody put up this, and then another person put up that. So you can get into an argument. But anyway, we'll do this. The other thing to say about conventions is that I won't use. So I'm not going to. So I won't use an lower plus upper indices. And just to say a bit, I mean, there's some more a little bit of an explanation in the book, but it's fairly standard in discussions of this to kind of work with upper and lower indices, which would correspond to component to vectors and dual and dual. So the question is, so there's this R4, and if you're going to do general relativity, if you're going to talk about curved space-time, you have to be very careful about whether you're talking about the tangent space to your manifold, to your space-time, or are you talking about the dual to the tangent space, the cotangent space. So you've got, if you have a curved space-time, you have to be very careful about, are you doing are you talking about this guy, or are you talking about the dual? And then when you have a metric, you can use the metric tensor to give you an isomorphism between tangent vectors and cotangent vectors. And then you use the components of the metric tensor so you use upper lower indices to tell the difference between vectors and covectors and dual vectors, and you use the metric tensor to raise and lower indices to give you an isomorphism between the two. And so people like to, in this subject, to kind of to take over that formalism for curve space and to work with to write down all sorts of formulas involving upper and lower indices, which correspond to talking about coefficients of vectors or covectors. And then then this guy, you say, well, there's a metric tensor which looks like -1, 1, 1, 1, 0, 0. And this guy, there's a metric tensor that looks like 1, -1. And then you keep these metric tensors around, whichever one your favorite one is, and you use these things to raise and lower indices to relate vectors and covectors. And so then there's always, at least in this formalism, then whenever you talk about the zero components of things, the time components of things, there's going to be an extra sign to worry about, which is depending upon, are you talking about vectors or covectors? And so anyway, so if you look at kind of most discussions of this, that's kind of they're trying to do that in order to try to kind of keep the computations clear. But if you stick to this, another reason for avoiding this one is that if you use that convention, you really have confusing signs, because there's a minus sign depending upon whether you're a vector or a covector, even if you're a spatial vector. Whereas here, you just have the minus sign to worry about if it's just the time component. But what I'll do instead is really just try to write down formulas that don't, you can think of everything as being just a lower index that I'm not actually, so I'm not gonna do this. The other reason, I guess, for doing that is, let me not say. The other motivation for adopting this kind of formalism is then you can kind of, if you have the kind of things where you've got upper and lower indices that match, you can kind of see when you're writing down expressions that are invariant under that are invariant under transformations that preserve these guys, which are the Lorentz group, which is what I'm going to talk about in a minute. So but I think what I'm doing, it should be fairly clear about what's invariant in the Lorentz group and why and what isn't. Okay, so that's just some general motivation, and also to explain what the relationship between this the way I'm doing this, and we may see this somewhere else. But but now the main thing that happens when you do this, so you're now talking about R4 with this weird inner product on it, and this is the space-time symmetry group. Is now, so before we just had SO3, we had just an SO3 of rotations, and so ignoring translations for now. I'll talk about translations a bit later. But ignoring translations, the space-time symmetry group is now just these generalized rotations, and it's rotations of R4 that preserve that inner product. And what I'll call it's called SO31. So I already kind of talked about this a bit before. It's that it's just the generalization of the orthogonal group, where you're looking at the thing it preserves standard inner product, but it's the one with signature 3 plus and 1 negative. Okay, so if we didn't have this weird sign, we would be talking about SO4 and standard four-dimensional rotations of the standard inner product in R4. But since we have a weird inner product, it's this group we have to get used to, and this is the called the Lorentz group. So when I say Lorentz group, it's going to mean this guy. And then I guess the other thing to say is that it's well, there's some other also so one thing to say is you also have O31. Okay. And so this is things. I guess I should be a little bit careful that the okay. So this has four components. Okay. So what I'm trying to do here is to I've mostly in this course tried to avoid talking about these discrete groups, like the fact that when you look at rotations, you can just look at the ones that are continuously connected to the identity, or you can realize that this group actually has several components, and these other components don't include the identity, but and you get them by doing things like by changing by doing a mirror reflection, by changing all the components to minus sign and changing the handedness of your thing. So here, in the case of ON, remember, so for let me just say it. So for ON, what I think we showed this, that there's really kind of two. There's SON, which is the things that have determinant 1, and then there's then there's another component of ON, which is the things that have determinant -1. So in the positive signature case, you have SON and this other component, which is another copy of SON, but it's rotations that also include a mirror reflection. Okay. This story is a little bit trickier. That if you say, I want to look at all things that preserve that inner product, you're going to have it turns out you're going to actually have 4 components. You're going to have this guy, the 1, which is which includes the identity. Okay. So we're really interested. When I say this, I really mean the component of the identity. But the tricky thing here is that
in this case, so the future is mapped to future, right?
Yeah. See, exactly. So what I want to say is,
and the other copy of SO31 is future to past, past to future.
Yeah. So here the point is you have to separately keep track of the change of changing the sign of all of what happens if you change the sign of all the positive of all of the space components. You get to a different component, but also separately, if you just change the sign of the time component, you get to a different component. So you get 3 other components. Because you change it because 1 by changing 1 time sign of time. X0, if you like, or all X. All. Yeah. So in the normal in the SON case, you just have 2 components to worry about. Here, there's 4 of them because there's there's the usual change the sign of everything, but there's also the thing that just changed this. So you're right. So there's something that you would, so one of these, there's another copy of SO31, which is all the copies of SO31 together with taking time to minus time. Okay, but that doesn't include the identity, right? So there's only one. Anyway, there's 4 components, but because in some sense, while you think you've made time and space behave in the same way, I mean, there really is, time still is kind of distinguishable in a way. There is kind of one direction you're treating differently than the others, and that that gives you extra components. Okay. So, but I'm pretty much going to avoid talking about these. I'm always going to be talking about this guy. And one of the reasons is also that pretty much all the methods that I'm interested in kind of working with are actually the algebra methods, and so they're based upon kind of looking at what happens infinitesimally close to the identity. And so anyway, you have to start doing some very different components. Sorry. Anyway, you have to do it to deal with these transformations. You have to you have to introduce some new and different ideas, and which I don't want to take the time to do. But a lot, and so these will be. This is what you want to talk about time. Often you want to talk about time reflection symmetry, and you want to talk about parity reflection symmetry, and those are so. There's a long discussion, a lot of books about the effect of that. But I'm going to stick always to this component. Okay, so now so what does this group look like? Anyways, let me just say so we're going to look at so thinking about these. So if lambda so we're interested in I guess I'm calling these for now lambdas as a group elements SO31. So one way of thinking about these things that they're really just there are four, you can think of them as 4x4 real matrices, and they're going to satisfy this kind of slightly weird version of orthogonality. That if normally you say that something is in SO4 if it's a 4-dimensional if it's a 4x4 real matrix, that's orthogonal, and you would say that means that its transpose and its inverse are the same. But another way of saying it is that let me say so these you have to write a slightly different condition than saying that the matrix its transpose is equal to its inverse. What you want to do is you want to say this. You want to say that it's transpose and its transpose and its lambda and its transpose. Lambda and its transpose, when you multiply them, you're going to get the identity. But what's here is not the identity, but this matrix. So this is the condition.
Then the right hand side should also not be the identity.
Oh, sorry. Yeah. Thanks. Yeah. Thanks. Right. Yeah. Thank you. That's right. Yeah. So you want things. You want linear transformations that preserve this weird inner product. Okay. And so in the case of if this were the identity, then this would just be saying that the transpose and the inverse multiply. Yeah. Anyway, this guy is the inverse of this guy, but instead you have this weird condition. Okay. If you want to think about these, one way, maybe a good way to think about these is to think about them as that there's first of all, think about a subgroup of these that you actually understand. So there's an SO3 subgroup. So you take things of the form, just leave time alone, and then do a spatial rotation, and then zero it. Okay. So if you just take so SO3 kind of sits inside this group is just to put just things which preserve the time direction, and so it's just 4x4 matrices of this form where R is our thought, R is SO3. So these are all the things you already know how to deal with, and that you're used to. So the interesting question is, so this is 3 dimensions of the group, and so there's kind of 3 other dimensions of the group which are going to mix together space and time. Okay. These are the three dimensions that just mix spatial components. Okay. And so maybe so what you want to do is let me just do this. So but you also have lambda, and is called that mixed space and time 0, and they're called boosts. And maybe if you want to, if you want to think about a rotation, it's a good idea to kind of break any rotation into to think about the rotations that leave one direction. Let's say that leave one direction invariant and are just kind of and just look at what they're doing in the other direction, and it's just a rotation of the orthogonal plane. So you can think of these guys as being generated by 3 different kinds of rotations: those about the 1-axis, those about the 2-axis, those about the 3-axis. Well, similarly, you can think about boosts as being ones that mix x1 and x0 and leave everything else alone, or things that mix x2 and x0 and leave everything else alone, or things that mix x3 and x0 and leave everything else alone. So you can think of them as a general element as being built out of those. And so for example, is the things that there you go. So if you look at what are the things that leave the 2 and 3 directions alone, and that just mix the 1 and 0 directions, well, they're going to be it's going to look like a rotation matrix in 2 dimensions, except because of this weird minus sign, instead of having cosines and sines, you have hyperbolic cosines and hyperbolic sines. So and I hope I've got the sign right, but there's a cosh phi sinh. I hope that sign's right. So things of this kind. So this is a standard. This is if you want to think about what a boost is doing, well, it's
I think there is these 2 are -1, and also here in the right bottom side, it's 1 and -1. I mean,
I don't think
I like lambda equals.
Okay, yeah. So the question is, should there be a minus sign here? That's right. You're wondering?
Well, I'm not sure, but at least you will have -1. Oh, maybe not. But
well, this is definitely right. Yeah. No, the only thing.
Sorry, my fault. Sorry.
You know, I'm pretty sure that I checked this. The only slightly confusing thing is if it if this were a rotation, and if this were a real rotation, this would be cosine, sine, and minus sine. So I think but I think there's no minus sign there. But I have to anyway.
Yeah, my fault.
Okay. Anyway, but these guys, so these guys are just basically exponentials. So this is not so phi is not an angular variable. It's phi is a real variable. I mean, this is not a periodic, and so boosts are things that you can kind of. I mean, they kind of correspond. They correspond to not to a rotation of the vector, but to kind of a transformation which kind of moves it arbitrarily close to the, corresponds to, if you think of it as a velocity vector, it's something that makes the velocity higher and higher, bigger and bigger, and then asymptotically approach the velocity of light as you go off to infinity. Anyway, so if you want to play, if you've seen the special relativity, you should have kind of seen it played around with these things. But just as a point of group theory, just if you want to kind of think about this group, it's a good idea to think about it that is generated by the three kinds of rotations you're used to here, and then three kinds of boosts like this. That's one way of thinking about it, if you want to get your hands on a specific element. Okay, so then what about the Lie algebra? Let me see how I want to. So Lie. So okay. Well, remember. So in the case of orthogonal groups in general, the Lie algebra of SON is just kind of all antisymmetric matrices, all matrices that are antisymmetric under reflection about the diagonal, and there's a nice basis, which is to take anything in the upper triangular part of the matrix and put a 1 there, and then put a -1 in the corresponding reflected place in the lower triangular matrix. So it's the same thing. So this has this. So what I'm going to do is I'm going to write. I want to write this. Yeah. So let's write. Let's write a basis. Which I'll call M of MJK, where J is equal to 1 to 4 to 4. Actually, I want actually, how do I want to do this? That's right. So K is equal to 1, 2, 3, 4. Or actually, I guess I'm doing it 0, 1, 2, 3, and then J is less than K. So it's gonna be the same kind of thing that I would do for the standard orthogonal group. It just I would define a bunch of elementary matrices here, and then let me write them down. And so the ones that are going to correspond to infinitesimal rotations, the things that leave the time direction alone, are going to be things like M1, M12. So this is an infinitesimal rotation in the 1-2 plane. So it leaves 0 alone, and then it does and then it, I guess in it's this guy, and then it leaves 3 alone, and then I'm not gonna write down the and this is what I was calling before kind of L3. So it's just an infinite. It's a rotation about the three-dimensional axis. It's also leaving time alone. Okay, and then anyway, and you can figure out what the other 3 of these are. The other 1, 3, and 2, 3. They correspond to rotating about the 2 axis and about the 1 axis. Okay. So this has dimension dimension 6. So this is a real vector space of dimension 6. Three of its basis elements are just the usual ones for that SO3 subgroup. But then you also have you also have 3 more, which are the things that you exponentiate to get the boosts. And the things that you exponentiate to get the boosts are n0. They're the things that have zeros in it, and there's like, so 0, 1. So now instead of having a 1 and a -1, you have things with the same sign here, and then 0, 0. And then et cetera. There's also going to be an M02 and 03. And I'm going to give these names. I'm going to call this K1. And I'm going to call this K2. And so this is the infinitesimal generator of a boost in the 1 direction. This is a boost in the 2 direction. This is a boost in the 3 direction. These are the usual. And so this is L2 and this is L1. Okay. So I'm gonna think of these basis elements of this Lie algebra as being given by the L1, L2, L3 basis elements of the SO3 subgroup, and this K1, K2, K3 what gives you the rest of the directions in here, and they're the things which exponentiate the boosts. Okay.
Question.
Yeah.
The SO3 subgroup here is normal, right? So does that mean that
No.
these
No.
generate when you exponentiate them, they generate the cosine?
No. Sorry, it's not a normal subgroup.
Okay.
So yeah. So you're going to have Let me write down the So there isn't a you can't just take it's something to watch out for. So SO you can think about SO3 mod up to SO3, but it's not a group. Okay, so you can't think of this as being anyway. You can't think of those boosts as giving you a group, because the problem is really going to be, and this is kind of what I wanted to say next. The problem is really just that K1, you can show. You can start computing what. So the way the commutation relations of the L's and K's basically tell you that K. So K vector transforms as a vector under the SO3. Okay, so if you want to, and this tells you what the infinitesimal commutation relations of the L's and K's are. But the thing which is different is that if you start asking what happens if I commute a K and a K, well, what happens is if you start computing, you'll get that K1, K2 is equal to is a rotation. So the commutator of 2 boosts is a rotation, and then et cetera. I won't write down the other relations. Okay. So this is not, anyway. It's not corresponds to the fact that K. Anyway, these things don't. The problem is these guys don't exponentiate to a group because their commutator is not a K, but it is an L. Okay, and so now, okay, so you can think of this. You can think of this guy as just it's the 6-dimensional thing where you've organized you've organized its directions into K vector and L vector, and something funny is going on that when commuting K vector with itself is giving you something in L vector, which is a bit weird, but you can do that. But it turns out that what you'd like to do is you really would like to actually separate. So remember when we talked about SO4, in SO4 we found out that SO4 was actually did break up into two pieces, into two SU2s, or spin 4 was two SU2s. And well, it turns out there's something similar happens here, but in order to get it to happen, you have to complexify. Okay, so here's what you do is, so there's a trick, if you like, which again, it requires going from this real Lie algebra to a complex Lie algebra. So you consider Lie SO31 and start throwing in complex linear combinations. And then once you can do that, and then AJ is equal to a half LJ plus IKJ, and then BJ is a half minus IKJ. So if you do this, then what you find is that the A now if you start computing AJs of themselves, you find things like A1, A2 is equal to A3. I won't write down the rest of it, but it's then the let me just say plus cyclic. So it's plus cyclic permutations of that formula. And so now you've got, when you're commuting two A's, you're getting another A. And if you do the same thing with the B's, you find B1, B2 is equal to B3 plus cyclic. Okay, and so what this tells you, and these are just SL2C. These are just so everything. These are now complexly algebras, but they're the computation.
So AJ and BK commute.
Yes, yeah, and then X. Yeah, then AJ, BJ, BK is equal to 0, right? X. And so what you find, so this implies is that the SO31, so the Lie algebra of SO31, if you complexify it, it becomes the sum of two Lie algebras, which is Lie SL2C okay. So you can break this up. Okay, so now, okay. So what you often see a lot of, I mean, this calculation is completely crucial in pretty much any book in which people are discussing, doing relativistic quantum theory. They're going to do this, but they often will say something very confusing, like that that this shows that SO31 is really two SU2s. Well, no, it doesn't show that. You have to be careful. Exactly what it shows is this: that if you complexify, then you break this out. But you have to watch out that when you're complexified, when you do this, you have to still keep track of where inside here is my original SO31. Okay.
Question about the right hand side. Why did you write SL instead of SU?
Because it's complexified. Remember, so this is the real. So this is the if you want. I mean, if you think of these as three directions, as a real Lie algebra, this is the commutation relations for SU2. But remember that you can't do that because I'm throwing in complex coefficients. So so I'm using here the fact that So if the fact that I'm complex, since I'm talking about, so recall this, that if I take the Lie algebra of SU2, which is a three-dimensional real vector space of things with this basis, if I complexify that, I get the Lie algebra of SL2C. So here, this guy is just the, all anti-Hermitian 2x2 complex matrices. But if I complexify, I get all. I also get the Hermitian ones, and then I get, and this is all 2x2 complex.
Okay.
Okay. So, I mean, it's tricky. It's tricky. Okay. But what's going to happen? Okay. And I want to say, let me see this. Okay. I don't want to say this. So what we're going to show. So what's true? So the claim. Let me try to. The next part of this, I'll try to start on this in the last few moments. So the claim is that the spin is actually equal to SL2C. Okay. So something funny. So this is what's gonna. So we want to understand. So the next part of this will be trying to show this. Okay. Maybe before I do this. Yeah, actually, maybe before I do this, let me just say a bit more about what happens at the Lie algebra level. So notice that if you take a real Lie algebra, and so what I showed was this, but the point is, if you take real Lie algebras of different signatures, if you change the signature here, when you complexify, you lose the ability to. If you've allowed yourself to throw in i's, there's no difference between the different signatures. So this guy is going to be the same. This is going to be the same thing as the Lie algebra of SO4 tensor to the C, or the Lie algebra of SO2 tensor to the C. I mean, they're all three of these, all these three different signatures. If I throw in complex numbers, I can't. There's no. I lose track of this ability of figuring of knowing where the minus sign is, because I can put in i's, and I always end up with this. Okay, and
well, so hard these guys related to the Clifford algebra looks like something quite similar.
Well, the Clifford, yeah. So the Clifford algebra is going to be, yeah. So the Clifford yeah. So there's a similar issue. Yeah, maybe I'll just say that. So what you're asking. So similarly, you found that the Cliff of 4C was which is what got if you took Cliff of 3-1 and answered or Cliff of 2-2 or 4-0. All of these were the same, and this was it was just 2 by all 4-dimensional complex matrices. Okay. So there's a similar. So this is really the same story as the Clifford algebras. Remember, the Clifford algebras had lying within them, if you look at the things that are quadratic in the generators, if you look at things that are quadratic in your gammas, that's going to be the Lie algebra of a rotation group. And so this story kind of lies inside this story, as these are the pieces of this story that have that are just, if you just restrict to things that are quadratic in the generators. Okay, yeah, and again, so there's something funny that so the point is, once you've thrown in the complex numbers, you've lost track of the difference between these three Lie algebras and between these three these three Clifford algebras. So these three Clifford algebras are actually all different. Okay, this one is actually the 4x4 real matrices, and both of these are actually 2x2. Both of these are actually 2x2 quaternionic matrices. But anyway, you've got three different Lie algebras, which when you if you complexify, they all become the same. They all become this guy. You've got three different Clifford algebras, which all become the same if you complexify, and they're just 4x4 matrices. And there's a similar thing. Maybe I should say, and before I do this, maybe more generally. So at the level of the groups. So groups, you're going to have SO 4C is SL2C. I should, sorry, and you have to go to the spin groups. Yeah, it's the spin 4C, 2C, SL2C. But there's three, there's this guy, but there's also spin 4, which is just the real thing, the real things. Remember, I showed you that was SP1 across SP1. That was SU2 cross SU2. Okay. And I showed, and the other thing is that spin of 2 is SL2R cross times SL2R. Okay. So as you change the signature, if you think about the real Lie algebras or the real groups or the real Clifford algebras, you get three different things. And if you look at the group, you also get three different groups. You get 2 copies of SL2R, or you get 2 copies of SU2, or you get 1 copy of SL2C. But the point is, if you now complexify and don't look at real Lie algebras, real Clifford algebras, or real groups, but look at complex ones, then you always get the same thing. You always get you get the Lie algebra SL2C plus SL2C. You get the group SL2C cross SL2C. You get the Clifford algebra, all 4x4 complex matrices. Okay. So this is the so physically this case is kind of nice. This case is kind of nice because you can understand everything and with nice and real numbers, so it's easy to deal with. But this one doesn't physically seem to have much significance. The thing that the kind of physical case seems to be this, and it's often interesting to kind of think about what happens when you change treat the time with the same get rid of that minus sign of the time, and then you're in this case. So you often end up thinking about this case, or you end up thinking about this case, or you often do calculations, by doing a so-called Wick rotation and going to the standard Euclidean signature and use this, but somehow physically in Minkowski space you want to get back to this, but you physically you never there's not much use to this real form that exists. Okay, so now before I finish, let me say this in a somewhat more in a more concrete way, which is going to be more useful for what we're going to do. So what we want to do next is to ask about the represent what are the representations of the Lorentz group, and it's going to be actually maybe to give it away. Once you know this, once you know that it's SL2C, then the representations of SL2C are basically it's the same calculation that we did before. They're all the spin 0, half, 1, etc. representations, or if you like, they're the polynomials in Z, in Z1, Z2. But the fact that it's not unitary, that it's SL2C, means that the representations are not equivalent to their conjugates, and so you have separate representations which are not unitarily equivalent, which are if you like, the polynomials in the Z1 bar, Z2 bar, the complex conjugate representations. So I'll talk about that next time, but that's what the finite dimensional representations of the Lorentz group are going to look like. But before I get to that, maybe it's a good idea to kind of get a nice way of seeing that this is true, that you can work with this way. And what we're going to do is generalize. So recall in the case of, so we showed SO S spin 4 equal to SU2 cross S, or maybe I called it SP1. And what I did was I identified R4 with the quaternions, and then I showed that you could get a linear transformation of the quaternions that preserved the standard the standard positive definite inner product on it by taking Q if you take a quaternion and you left multiply it by another quaternion and right multiply it by a second quaternion, preserves there's the inner product if Q1 equal Q2 equal to 1. So if these were unit quaternions, then if these were unit quaternions, so Q1 and Q2 are elements of SP1, are unit quaternions. So left and right multiplied by unit quaternions preserved the standard notion of distance, and so and you use that to show that that any and so you could get a rotation, something that preserved the four-dimensional notion of distance by doing this, and you ended up with spin 4 because if you put in a minus sign on both of them, you would get the same rotation, but this gives you the double cover. So what we want to do here is I want to kind of generalize this trick, and instead of identifying R4 with the quaternions, so instead identify R4. How do I want to do it with let's see. How do I make sure I got this right? Yeah, with the now how do I want to? Okay, with self-adjoint with R4 with self-adjoint. To my complex matrices. So what you want to do is you want to identify x0, x1, x2, x3. What you want to identify this with? How do I set this up? with x0 plus x3. And then you've got x1 minus ix2. So the kind of fundamental idea here is to try to do something something similar to what you did here. And then what's going to happen is now what happens is the so what I want to call this a matrix. So this matrix and I guess I've got it. So x0. So the thing, another argument for the opposite side is that what you find if you take the determinant of this guy, this times this minus this times this, you get that this guy, e squared, is equal to minus x squared. It's the determinant. Okay. So one nice aspect of this identification there's really a good argument that that what you really should be thinking about when you're thinking about Minkowski space is not R4 with this weird metric, but Hermitian, the space of 2 by 2 Hermitian matrices, the 2 by 2 self-adjoint matrices with the determinant as the metric. That's another way of saying what Minkowski space is. And the nice thing about that, this thing gives you a nice way of understanding how the SO3-1 is going to act. Because what you do is you show that that if omega is an element of SL2C, then this guy, so well, x0 plus x3, x0 minus x3. Goes to omega transpose preserves. This preserves the determinant, thus the inner product. And it also preserves takes self-adjoint and I think you may have seen this calculation in the first semester. I was actually on a problem set. It was something like this. But basically, so the idea is that if you that morally the argument is that you really should think of Minkowski space as 2 by 2 self-adjoint matrices with the inner product, their determinant, and then if you want to understand how the Lorentz group acts, you just look at the at multiplication on one side by an SL2C element, on the other side by the adjoint matrix, and because they're both in SL2C, they'll preserve the determinant, and because you have the adjoint here, they'll preserve the adjointness. If you take the adjoint of this guy, the adjoint of this guy is equal to himself. And so this shows anyway, this really shows then that this and you get a double covering that omega and minus omega will give the same rotation. So this really is what shows that spin 3-1 is equal to SL2C. And then once you know this, I mean, so you have the represent you see how this acts as rotations on this R3, but R3 is thought of as in this weird way. But in addition, just like in the four-dimensional case, this also now, once you've identified your double covers of rotations as being 2 by 2 complex matrices, this also gives. So this gives this the spin representation on C2. Yeah. So if you just think about SO31 as these 4 by 4 matrices, you can't see the spin representation. But if you think of these Minkowski space version rotations as being SL2C is doing this, then you can see that these guys are going to also act on C2, and you're going to have spin representation. Okay. So I'll stop there now, and the next kind of, anyway, we'll get back to it. So that the next time we'll talk about kind of what are the representations of the Lorentz group, and then get started. And then the next part of it is then to add in the translations, and you have the Poincare group, and then we can generalize everything that we were doing about representations of E3 to representations of the Poincare group, and you can then kind of build your kind of ideas about relativistic quantum mechanics on that. Okay, so are there any questions about any of this? I mean, this is a bit this business about how the complexification works, and the fact that you've got different real forms that under complexification become the same thing is, I should say, it's confusing at first, and it's kind of remarkable if you go and look in almost any kind of quantum field theory book about this, you'll find some version of this calculation, and you'll often find some very strange and confused this discussion of what the relations of these objects are, because the fact that you're complexifying, the fact that there's a complexification going on is crucial, and you're doing something, and you have like this weird phenomena that the complexification of SL2C is 2 copies of SL2C. So you have kind of mysterious things like that happening, and it's if you're not used to thinking about in terms of a different real forms complexifying to something, it's hard to see what's going on. But once you take that point of view, I think it does clarify a lot of this. Okay. Okay. So any other questions? Okay. So again, I'll be around. So please stop by and connect to the other Zoom session, and if not, if I don't see you, have a enjoy taking the week off, and in terms of all you have to do is just try to see if you're caught up on what we've been talking about and things you don't understand. If you have any questions, contact me. We can talk about it, and if not, I'll see you a week from Tuesday, and we'll get deeper into relativistic quantum mechanics. Okay, bye then.
Thank you.